Okay, good afternoon. So this is our 17th lecture. In the previous lecture, we have already started our discussion on the flow over spheres at high Reynolds number, and today we will continue that discussion. And previously, if you recall, I told you that when we are considering the high Reynolds number, then we cannot avoid the advection terms from our governing equations. Okay, so that's why we are having inclusion of non-linear terms into our analysis. So that's why finding the exact analytical solution of the equations using non-linear terms is actually challenging. So that's why the experimental and simulation approaches are already there, but two ad hoc approaches which can give the quick solution is, first approach is what we can do, we can actually apply the boundary layer theory, and by using the boundary layer approximations we can calculate the analytical or theoretical solution. Okay, and the second approach is use of, when you are performing the simulations or numerical methods, then one simplification you can do, you can take the help of axisymmetric approach, because sphere is a symmetrical shape. So that's why if I consider the axisymmetric approach, then my whole analysis will become nothing but two-dimensional. And in this two-dimensional approximation, what we will be having? In this two-dimensional approximation, I can use the Stream-Vorticity method. Okay, because stream function and vorticity function are actually applicable for two-dimensional flow field. So whenever we are having two-dimensional flow field, then use of this function, stream function and vorticity field, these gives us nothing but the lesser number of variables. Okay, so these will be making our analysis more simpler. So about the first approach, which is based on the boundary layer approximation, I have given you some idea in the previous class. Today quickly we will try to see first the application of stream vorticity method for a two-dimensional Cartesian approach, and then we will try to see it for the spherical system. Okay, so for a Cartesian approach, if I have two-dimensional steady incompressible condition, okay, so under this scenario what will be happening? We will be having our, this as the continuity equation, and this will be my momentum equation. One important point here, steady assumption is not invoked because del u by del t and del v by del t term is there, so that's why it means that we are not having yet inclusion of the steady assumption. Okay, now what we need to do is, I need to convert these equations in terms of the stream function and the vorticity field. Okay, so have you all studied this stream vorticity method, those who studied the course on CFD in your previous course? In the last semester you were having the course on computational fluid dynamics, so there you might have studied stream vorticity method. Okay, and maybe to some extent if AFM you were doing, it might have been even discussed there as well. Okay, so what we do in case of stream vorticity method, our aim is to write these equations in terms of stream function and vorticity function. Okay, vorticity field. So stream function is u, I will be replacing with del psi by del y, and v I will be replacing with minus del psi by del x. Okay, but whenever we will be doing so, my continuity equation will be inherently satisfied. So what I need to do, I need to now find the corresponding form for momentum equations. Okay, and in momentum equations our first aim is actually to get rid of the pressure term, because pressure field will not be known a priori. We will be only having the knowledge of the velocity field, from which I can calculate the values of psi and values of omega, which is vorticity field. So because I don't know the conditions for pressure field, so that's why I want to actually get rid of the pressure term initially. So what I will do, this is my x momentum equation. I will take the differentiation of this x momentum equation with y, and I will take the differentiation of y momentum equation with x. Okay, and so this is nothing but identical to the divergence operation on this. Okay, so in biharmonic case we have done some divergence operation, so that operation actually I am doing over here. This first equation is del by del y and second equation is del by del x. Okay, and after doing this operation, then what I will do, I will actually subtract one equation from the other. So if I do this subtraction, then ultimately what I will be getting? I will be getting del omega by del t plus u times del omega by del x plus v times del omega by del y equal to mu by rho will become nu times del square omega by del x square plus del square omega by del y square. So you can see now in purely your equation is actually in terms of omega, and you have some component of u and v in the advection term which can be replaced with these quantities u equal to del psi by del y and v equal to minus del psi by del x. Okay, and you know the definition of omega for a two-dimensional flow field is nothing but del v by del x minus del u by del y. Okay, and another thing, in this definition, if you substitute the value of u and v, what you will be getting? You will be getting one Laplacian of stream function is equal to minus of vorticity field. Okay, so this is also something which we will be getting over here. Now, so this is, and these u and v you can replace with psi. So now these two has become nothing but your equations purely in the form of psi and omega. So now instead of the variables u, v, p, u, v, p, how many variables were there? 3. Now we have only 2 variables, psi and omega. Okay, and earlier you were having 3 equations, continuity and 2 momentum, which were little bit more difficult to solve. Now you have only the 2 equations, so you can more easily solve these equations. Okay, and now the question comes that ultimately once we calculated the values of psi and omega, then we need to calculate pressure also. So how to calculate pressure? To do that, what I will do now, I will take differentiation of this equation with x and differentiation of this equation with y, and then I will add these 2 equations. So once I do so, I will be getting the Laplacian of pressure is equal to 2 rho times this term, and this term can be written purely in terms of stream functions. Okay, so it means that if you know the stream functions, you can simply calculate your pressure field. Okay, is this one clear? So this is nothing but for a two-dimensional Cartesian system, and ultimately whenever we try to solve this type of equations, you can solve in dimensional form, and we also try to take the help of dimensionless form. So if you see in dimensionless form, then this is the first equation. This is the first equation in dimensionless form. Okay, means this particular equation. This equation is in dimensionless form. Then I have second equation in dimensionless form. And ultimately, this is the pressure equation in dimensionless form, and ultimately these are my non-dimensionalization parameters. Okay, so if I do capital U, U by U naught, X is X by L, P is P by rho U naught square, and V and Y are similar way we have done, and tau we have defined nothing but over here the viscous time scale. So mu naught into T divided by L. So reference viscosity into time divided by L. So this has become nothing but a viscous time scale, and your this is dimensionless vorticity, omega into L by U naught, and psi, small psi by U naught into L is capital psi, which is dimensionless vorticity, and ultimately you will be finding in first equation you are having 1 by Re terms where Reynolds number is having the usual definition. Okay, so this is nothing but these equations now in dimensionless form. So what I suggest is that, because all of you have some idea of the computational fluid dynamics and finite difference approach, I think all of you have studied in very much detail. If you don't know about the finite volume or element methods, then at least finite difference approach all of you know very well. So what you can do is, you can take a simplified two-dimensional case of flow over a flat plate of length L, and then you can solve it in dimensionless form, considering say you are doing this analysis for Reynolds number is equal to 500 or so, and you can decide your domain size in dimensionless coordinates and then write the finite difference code to actually solve this system of equations. So try this, because whenever I am just conveying you in the class that this is how it can be done, though you have some idea, okay, these are the equations, but you are not getting the exact feel that how output is actually coming. Okay, so if you try solving it, then you will be able to feel that how these equations can give you the results whatever I am showing actually in this in these lectures from some existing literature. Okay, so that's why my advice to all of you is, for considering a two-dimensional situation of flow over a flat plate and considering some moderate value of the Reynolds number, so that you don't require much computational power, try to solve this system of equations. Okay, all of you know finite difference method very well, and whenever you are finding any difficulty, you can contact me, or even among you also some of your friends may be good in programming or so. Even you need not to go for programming. So first of all, if you find that difficulty that you people are not having good programming skills, first you can start solving it on a paper. Okay, what you need to do is, you need to first discretize these terms. You know this is convection term, so use for this term backward difference scheme. Okay, use for this term backward difference scheme, and for these terms go for the central difference scheme. Okay, so for diffusion term you can go for central difference scheme, and for these you can go for backward difference scheme, and in the starting avoid temporal term, just consider the steady flow situation. So just solve this system of equation, only take say 20 number of grids, that's it. Take a very coarse mesh and solve it on a paper. So once you are able to see the data, okay, that you are able to calculate this data, then only you will be getting a proper feeling that you are able to do this. So what I will do, because I have planned the course that initially I will talk about theoretical approaches, then so maybe around up to 23rd or 25th lecture mostly I will be talking about the theoretical approaches. Then from 25th to 30th lecture, 5 lectures I will be talking about experimental approaches, and then 10 to 12 lecture I will be talking about the numerical approach. And whenever we will be discussing the numerical approach, maybe for 1 or 2 cases I will try to show you some of the codes where you will be seeing the output, and few cases we will also try to see using some commercial software packages, okay, of multi-phase flow scenarios. Okay, is this one clear? So maybe after 30th lecture there may be little bit more of hands-on sessions, say after 4 or 5 classes. Once we discuss the theory of the computational method in the class, then after that we can have 1 or 2 hands-on sessions. Okay, so but what I am suggesting is, now itself also you can actually, because while we are discussing the pure theoretical approach, then also we have many limitations, because theoretical solutions are not applicable for all scenarios. So that's why there also we are trying to take the help of numerical things. So it's better if you start practicing and then try solving for some simplified scenario, then you can go for the complex things. Okay, because you will get some hands-on experience that how things are being done, and whatever outputs I am showing over here, you can also generate these outputs if you solve this set of equations. Is this one clear? So of course whenever we have to go, so the previous 2 slides I just included to show you that this method for a 2-dimensional Cartesian system, because we all are familiar to the Cartesian system and we can easily recognize what we are doing over here. But whenever we deal with the spherical or cylindrical system, we are a bit less familiar, because we do number of problems in these systems bit less. So, but ultimate, because we are talking about flow over a sphere, so whenever I am considering the flow over a sphere, I have to deal in nothing but the spherical coordinate system. That is the most idealistic one for this situation. Okay, so that's why whenever I will be writing the corresponding equations in terms of stream function and vorticity field, I will be writing in terms of the cylindrical coordinate system. So it means I am writing in r theta plane. Okay, so in terms of r theta plane, this E is nothing but identical to delta. So wherever I am using E symbol, it is identical to delta whenever it is being used for the spherical coordinate system. Okay, so E square of psi, so this psi is dimensionless stream function and Z is dimensionless vorticity field, which for spherical system is defined as zeta, which is vorticity, into A is radius of the sphere divided by u, where u is free stream velocity. Is this one clear? So this is one equation, and the other equation is this one. Okay, so these are the two equations for steady two-dimensional axis symmetric flow over a sphere. Okay, now whenever, so what is this equation? This first equation is coming from, in Cartesian system, equivalent form is Laplacian of psi equal to minus of omega. So that is in Cartesian system, and corresponding form is this. And then this was the other equation where we were having involvement of psi as well as vorticity. So this is the vorticity field and this is psi. U times, what was the equation? U times del omega by del x. So in place of x, here will be r sin theta into del by del theta. Okay, in spherical coordinate system. And z is in place of omega. And this psi is, as usual, replacement for u. Okay, so this is my second equation. Point is clear? And of course, these two equations are in dimensionless form. That's why in the denominator you are finding the Reynolds number. So now can you make the equivalence from the Cartesian system? So Cartesian system, I have already shown you the derivation. So here also, if you take your generalized continuity momentum equations in spherical coordinate system and then follow the similar operations, you will be getting these dimensionless form of equations. Okay. Here, so definition of Laplacian is, in spherical coordinate system, this is the definition of the Laplacian. Okay. And of course, when we are non-dimensionalizing this capital R, we are considering as small r by a. Okay. So what we need to do now, we need to supply the boundary conditions. Can you tell me how many boundary conditions we need to supply now? How many boundary conditions we need to supply? Please tell me. How many boundary conditions for this system of equations we need to supply? Only two. So you can see over here I have a term E square. Okay. Here also I have E square. And if you see in E square, I am already having del of square here. Okay. And order of this equation is what? What is the order of this equation? Only second? First in R. Okay. So we need to supply what type of boundary condition? If you have flow over a sphere, it is not always necessary that for R there will be Dirichlet or for theta there will be Newman. So that is depending upon the physical situation. Okay, so it is not always required that for certain parameter only Dirichlet is needed or only Newman is needed. So boundary conditions will be always dependent upon the physical situation. Okay, so here what we will be considering, at R equal to 1, you have a solid sphere. No streamline will be entering. So stream function will be having a constant value, and that value I am assigning equal to 0. Okay. You have a sphere. At the sphere I will be having no slip boundary condition. So del psi by del r is equal to 0. Tangential velocity is 0. When you are away from the sphere, when you are at large distance away from the sphere, then what is the condition? Free stream velocity is known to you. Okay. So if you see at r approaches to infinity, then psi by r square will be approaching to half of sine square theta, where the psi and r already including the free stream velocity capital U. Okay. Is this one clear? So that is something, the way I have told you in the system, when you are talking about the biharmonic equation, so this is the sphere and one coordinate is r, another one is theta. So I am having one ur and u theta. So whenever I will be calculating ur and u theta at this location, these will be in terms of sine and cos. So ultimately that is giving me this particular boundary condition. Okay. All are clear with this point? In addition, two more conditions are specified over here. What is the reason? That whenever flow is approaching to sphere like this, then particularly at this point I have a stagnation point. So psi is equal to 0 and vorticity is also equal to 0 at this point. Okay. Similar thing will happen when flow is separating out. At this point also we have some symmetry about this point. So because of that symmetry at this particular point also we will be having vorticity field and stream function value equal to 0. Okay. Now of course, so this is the system of equation for steady flow, and whenever my interest is only to see the final steady velocity profile of the system, then I will be solving this system of equation. But if my interest is to know that how flow is actually evolving before reaching the steady state, then I will be interested in time marching solution. Okay. So once I am interested in time marching solution, then this one additional term will be coming to this equation. So if this is equation number 2, in the left hand side of equation number 2, I will be having one more term, and this will be the term over here. Okay. Is this one clear? So, and of course the T star here also I have defined as Tu by A. So in the previous Cartesian system, whenever I have defined the time scale, there I have defined considering the viscous time scale. Here I am defining simply U by A. So here I am defining the inertial time scale. Okay, based on the velocity. Is this one clear? And of course, once you know the values of psi and omega, then you can calculate the value of pressure field. So if you know the value of pressure field, then what can you calculate? You can calculate coefficient of form drag and coefficient of viscous drag, because if you know the psi and omega, you can calculate pressure field. Okay. Once you know the pressure field, if you integrate surface pressure field over sine 2 theta d theta from 0 to pi, you will be getting nothing but your drag coefficient for form drag. Okay. And if you know the velocity field, and if you supply over here what? Wall shear stress, and wall shear stress can be easily written in terms of vorticity field. Okay. Wall shear stress can be written in terms of vorticity field. So if you write in terms of vorticity field, so this is the equation for the skin friction drag. Is this one clear? All are clear with this point? Because ultimately our interest is to determine the resistance forces, and by using these relations we can actually calculate the resistance forces. So unless or until you give a try by your own, so if you try solving the situations by writing codes, then you will be able to appreciate these points in better way. Okay. Okay, so quickly I told you about the flow over sphere. So now whatever after this I will be discussing, that will be nothing but the key findings of either this numerical approach or of boundary layer approach, or coming from experimental evidences, which will be just giving the what are the key characteristic features of the flow. Okay. So in this case we have flow from right to left. Okay. So in this case you can see that when my Reynolds number is very small, streamlines are almost symmetric. But once the Reynolds number is increased, so here you can see the bending of streamline is actually different. So it means that in this second case I will not be having the same pressure recovery as I am having in the first case. Okay. Then if I go to slightly more higher Reynolds number, then I will be finding that I am having a formulation of attached vertical structure just in the downstream of the spherical body, and then I am having the separation of the boundary streamline, something like this. So at this point I am having actually separation of the flow. Okay, and then when Reynolds number is further increased, then this separation point is actually shifting towards the upstream direction. So this ring, this circular ring which is actually growing at the rear of the body, this is growing in size and it is trying to shift the separation point towards the right. Is this point clear? So this is the basic feature. And in terms of vorticity field also you can see, so this is the contour of vorticity field. So in case of low Reynolds number, your vorticity field, though it is convecting towards the downstream direction, but still it is coming closer to the symmetric field. Whereas in the cases where Reynolds numbers are significantly high, then you have faster convection of the vorticity field towards the downstream direction. Okay. And here you can see the nature of the dimensionless vorticity field. So as per the Stokes hypothesis is applicable for creeping flow. Okay. As per Stokes hypothesis, we should have symmetry about the center. But in this case, you will be finding when my Reynolds number is increasing, my highest magnitude of the vorticity is actually growing, and this is shifting towards the occurrence of early angular positions. Okay. And again, one interesting fact you will be finding that whenever you are moving towards the higher Reynolds number, then in the backward direction you have again significant magnitude of the vorticity, but in the reverse direction. So that significant magnitude is actually coming because of the growth of the circulation eddy. So you can see this is a one circulation eddy here, and this circulation is actually growing in size once my Reynolds number is increasing. So as this is growing in size, one dip you will be experiencing in the vorticity field at just before the separation point, and then major dip you will be experiencing at the separation point. Okay, and then again vorticity field will be becoming 0 at this point. So this is nothing but the surface vorticity field. At the surface, how vorticity is actually varying. And then you can see the pressure field. In terms of pressure field, this particular line is corresponding to potential flow theory. So as per potential flow theory, we have inviscid situation. So in case of inviscid situation, if you start with some value of pressure at theta equal to 0, you will be able to reach the same value of pressure at theta equal to 180. So as per potential flow theory, you can see this is your profile of pressure. Is there some issue? So as per potential flow theory, lines should follow the same thing. Okay, I think in the right side scale is actually different. So just follow the scale of left side only. So in right side scale is different. So that's why you just try to follow the scale of left side only. So this curve is starting from here and then reaching here, and corresponding to this on left side I am having value equal to 1. Okay, so it means I have complete pressure recovery if I have inviscid flow situation. But on contrary, if you consider your Reynolds number equal to 10, for Reynolds number equal to 10, your pressure is starting at close to 2 magnitude, and then you can see it is below 0. So it means you don't have pressure recovery. Okay, and when you are increasing further Reynolds number, then corresponding to Reynolds number of 100, again you are actually finding some pressure recovery, but it is not actually the complete pressure recovery. Okay, is this point clear? So whenever your Reynolds number is actually being increased, so we will be having the effect of viscosity, and because of the viscous effect actually we will be having the formation of vorticity, and streamline will not be following the exact curvature as streamline has followed in the upstream direction. Okay, so if curvature of the streamline in upstream and downstream direction are different, then we will be having difference of velocity field as well as the pressure recovery will also not be possible. Okay. So whenever the flow evolves over a spherical body, it can be actually categorized into 6 different regimes depending upon the values of Reynolds number. So first is called as unseparated flow. When Reynolds number of the flow is from 1 to 20, then it is called as unseparated flow. So corresponding depiction you can see over here. So this is a very generic schematic representation in terms of dimensionless size of the sphere and dimensionless settling velocity of the sphere, and corresponding values of the Reynolds number are represented over here. Okay, so in this sphere you can see when Reynolds number is less than 1, corresponding to that you will be having completely laminar dominated boundary layer and we will be having no flow separation. Corresponding to Reynolds number equal to 20, we see there is formation of small vortices at the back, and these vortices will try to shift the streamlines away from the rear stagnant point. So this is nothing but my rear stagnant point. If in the rear stagnant point close to this I have formation of vertical structures, these will displace the streamline away from the rear stagnant point. So this is onset of separation. So regarding onset of separation, there are multiple theories. Some people concluded that separation starts at Reynolds number equal to 10. Some people concluded that separation starts at Reynolds number close to 30. Some said at 25. Then one of the major finding was that experimental evidences showed that separation occurs close to Reynolds number of 24. But it was found that the experiments which were done to found the separation point at Reynolds number equal to 24, when these experimental data were extrapolated in order to reach the zero size of the vorticity, this particular vortice which is just forming in the near the stagnant point, rear stagnant point. So corresponding to that, extrapolated value of Reynolds number was actually close to 20. So that's why 20 is considered as the separation, flow separation Reynolds number for flow over a sphere. So this is the Reynolds number at which the formation of smallest vorticity, smallest sized vorticity field will be actually, this vertical structure will be generating near the rear stagnant point. Okay. And then we have steady wake region. So in case of steady wake region, you will be having this region from 20 to 130. So in this region, you have formation of vertical structures, but you don't have so much oscillations in the rearward portion and your streamlines are actually smooth. Okay, is this one clear? Then we have fourth regime. This is onset of wake instability from Reynolds number of 130 to 400. So in this region what happens, now this streamline is not smooth, but it is having formation of small surface oscillations. So you can see these are the vortices, a number of vorticities, a chain of vorticities are forming, and then whatever the streamlines which are separating the mean flow from these vertical structures, that particular streamlines will be having some waviness. So that is called as onset of wake instability. Okay, and once these waves will be growing in size, what these will be doing? These will be breaking the vertical structures and you will be having a very chaotic situation. So Reynolds number greater than 400 and close to 3.5 into 10 to power 5 is considered as high subcritical Reynolds number range. So in this range of Reynolds number, you have actually this type of situation. Okay, and after this point you will be having critical transition and supercritical flow once Reynolds number is greater than 3.5 into 10 to the power 5. And then you will be having more extreme turbulent situation. So why these two are actually separated, there are certain reasons. So what we can see is that majority of the time you see flow behind cylinder or flow behind sphere, you are having formation of oscillating vertical structures. Okay, if you see some animations of experiments or numerical simulations. Okay, so at Reynolds number of 400, these vertical structures starts setting off from the sphere. Okay, and on in a periodic manner at some constant time interval, these vertical structures keep on leaving the rear portion of that particular surface. Okay, and this process keep on continuing, and in this range of process actually you will be finding that your separation point is actually coming towards the top side. Okay, but for Reynolds number greater than 3.5 into 10 to the power 5, you will again find that you have very chaotic vertical situation, but separation point is actually shifting again towards the backward direction. So that's why these 2 points are actually, these 2 ranges are demarcated separately. Is this one clear? So in one case what is happening? Vertical first appearance of the vortex setting is actually coming, and in second case the separation point which were moving first to the forward direction, that again started moving in the backward direction. Okay. So here you can see when the flow separation happens. Do you know separation condition, flow separation conditions from your basic fluid mechanics course? Eddy formation, yes, but what is the quantitative criteria at which we can say that flow separation has started? Sorry? Pressure is less than? No, that is cavitation. We know that 2 things, one is called as favorable pressure gradient, other is called as adverse pressure gradient. What is the difference between the two? If I have a converging section, what will happen? I am having a converging section. If I am moving in the downstream direction, velocity will increase and pressure will decrease. So it means pressure in the downstream direction is low and pressure in upstream direction is high. So that is considered as favorable pressure gradient, because whenever flow is approaching in the downward direction, pressure is also decreasing. And that is the obvious thing, that also every flow wants to have favorable pressure gradient to want to travel from high pressure region to low pressure region. But if you take a diverging section, what will happen? Pressure will increase. So though flow is happening from left to right, but pressure is increasing. So that is called as adverse pressure gradient. So very first condition for flow separation is, it will always occur when our dP by dx, if I have a pipe and x is along the length of the pipe, so when dP by dx is greater than, if it is less than 0, it means that downstream pressure is low, but if it is greater than 0, it means downstream pressure is high. So that is called as adverse pressure gradient. Okay, so you can see this first figure, this is corresponding to favorable gradient. So in case of favorable gradient, my dP by dx is less than 0. And here if you see the gradient of u with x, du by dx will be always greater than 0. On contrary, corresponding to 0 gradient, my dP by dx will be 0 and du by dx will be 0, where u is nothing but free stream velocity along the x direction. Okay, now this is third condition. Here I am having dP by dx greater than 0. Here du by dx will be less than 0. When pressure is increasing, then velocity will be actually decreasing. Okay, so in this scenario you can see this is called as weak adverse pressure gradient. It means when dP by dx is not very high. its value is positive, but it is close to 0. But once its value reaches a condition such that my wall shear stress at this point is 0, then after this point, if I even go for small increase in the pressure gradient, I will be having actually flow reversal. So my velocity profile will become something like this. So you can see this was the original velocity profile. Now this is the new velocity profile, and this is the next point of the velocity profile. Is this point clear? So it means separation point comes corresponding to wall shear stress equal to 0. Now from our condition we know that del T by del Y at wall can be written in terms of mu times del square U by del Y square. Okay, and in terms of pressure, this shear stress will be equal to dP by dx, and dP by dx outside the boundary layer region can be written in terms of minus rho u into du by dx. Okay, so when this second gradient at the wall is 1 by mu into dP by dx, it means it is giving me the point of inflation, okay, where slope is actually changing. So corresponding to that, I will be having, when second derivative is positive, corresponding to that I will be having actually walls change in slope of the wall shear stress, and corresponding to this point I will be having wall shear stress is equal to 0. Okay, and immediately after this critical pressure, if I increase the pressure, then I will be having actually backflow. Is this point clear? So typically you can see if you have a converging diverging section, then what happens? What happens in converging diverging section? Velocity is increasing first, and after this velocity is decreasing. So once velocity is decreasing, the point at which I am having flow separation, here I will be formation of vertical rings, and after this point actually my only this much portion will be leading to effective portion for flow, because here I am having formation of stationary rings. Okay, so here this type of circulatory pockets in the flow will be actually appearing. So major effective area of the flow will be only this much. Okay, so this is the reason that if my angle of divergence is very high, then separation point will be coming actually very early. So this is the reason whenever we have this Venturi meter, okay, so Venturi meter is also nothing but a converging section, a constant section, and then a diverging section. So the angle of the diverging section of the Venturi meter is actually not kept beyond 6 to 7 degrees. Yes. Okay, it is not kept beyond 7 degrees, because if you keep it beyond 7 degrees, then you will be having significant, you will be having flow separation, and effectiveness of the Venturi section will be decreasing, and of course there will be more losses. Okay, operational cost will be high. Second important application of this comes in actually design of wind tunnels. In wind tunnels, what we have? In order to achieve the Mach numbers greater than 1, first we have a converging section, and then after that converging section, ultimately we have to discharge that air to the surrounding atmosphere. Okay, so for that we have to have one diffuser section. Okay, so if you consider this to be diffuser of a wind tunnel, and if you have formation of backflow, so your efficiency of diffuser will be decreasing, because only this much portion is now effective, and this portion is actually, yes, this major portion of the diffuser is actually covered by stagnant pockets in the flow. So the efficiency of diffuser will be decreasing. Why efficiency of diffuser is important in the wind tunnels? Because when you are operating flow, allowing the air to flow at Mach numbers greater than 1 or close to Mach number of 5 or 6, then your power required to operate the pumps or axial fans is actually very, very high. So if your efficiency is poor, you have small pressure recovery, then your operating cost will be high. Okay. So this is something regarding the onset of separation point. So you can see in case of laminar flow, this separation comes close to angle of 82 degrees. But when flow becomes turbulent, then again separation point shifts towards the larger angles of close to 120. Is this point clear? And remarkable change in the separation point you can see in terms of this pressure coefficient. If you plot it in terms of theta, then for inviscid theory this is complete pressure recovery. For laminar flow, pressure recovery is less, and for turbulent flow, pressure recovery is even bit better. Why? Because my separation point for turbulent flow is shifting little bit towards the rear end, and I am having in more portion of the sphere I am having actually attached streamlines. Is this point clear? So you can see the corresponding experiment of dropping a spherical ball into a liquid. So here you can see this is the laminar situation. So separation point is somewhere here, and here you have separation point somewhere here, which is a turbulent situation. Is this one clear? Then you can see the separation angle. So how separation angle changes with Reynolds number. Okay. So in the range of 10 to power 5, your separation angle keep on decreasing when you are increasing your Reynolds number. And in the range of Reynolds number 20 to 400, so 20 to 400 is the region in which you have formation of vortical structure, but vortex shedding is actually not taking place. So in this region 20 to 400, in this particular region you can actually specify, you can calculate separation angle using this particular logarithmic profile. So here you can see the profile of the curve is actually logarithmic, and when your Reynolds number is 400 to 3 into 10 to power 5, if you have to fit the data for complete, then you can see this is following nothing but a complete power law like profile. So with the help of this power law equation you can actually calculate the separation angle. So now if this equation is given to you and if value of Reynolds number is given, then you should be able to calculate the value of separation point, and corresponding to that if any other information is required, that also actually you can calculate. This is the dimension of the wake length. So whatever the portion in which your vertical structure is actually growing behind the this vertical structure is growing behind the sphere, the length of this particular portion after again streamlines are actually reattaching and coming close to line of symmetry, that we are calling as length of the wake. So if length of the wake is non-dimensionalized with diameter of the sphere, then you can see how with Reynolds number it varies. So you can see with Reynolds number actually it is growing in size, and once you are seeing the minimum size is corresponding to Reynolds number of 20. So it means Reynolds number of 20 is the point at which actually vertical structure first starting appearing near the rear point. So this is the point corresponding to onset of flow separation. Is this point clear? And then this is the volume of the wake. So this is the volume of the wake as function of Reynolds number. So whenever the very early experiments were done, then it was very difficult to determine the exact size of the wake close to 20. So this data of Kalra and Heller, this was used to extrapolate this particular graph, and when this graph was extrapolated corresponding to Reynolds number of 20, we were getting nothing but zero size. Okay. This is one important information. So as I told you, I have included here a video of vortex shedding, but this graph, I think internet is not connected to the system at the moment. So this is a YouTube source. So what I will do, I will upload this. This is a hyperlink over here, and I will post this video. I will post this lecture on Moodle. So in the Moodle, you can click on this link, and then you see a video of vortex shedding from a sphere. So if you have to determine the frequency of vortex spreading, so it can be non-dimensionalized in terms of Stroll number, and Stroll number gives F into D by V. So this is the definition of the Stroll number. So you can see when the Reynolds number is actually increasing, your vortex shedding frequency is actually increasing, and it is reaching the highest value corresponding to Reynolds number of 2, 3, 4, 5. So close to 5 into 10 to power 3. Okay. So close to 3.5 into 10 to power 3, it reaches the highest value, and then again actually it start slowly decreasing. Okay. Then this you can see the corresponding value of again surface pressure for wide range of Reynolds numbers. So here one important point is, whenever you are considering the Reynolds number of, so this D, Reynolds number of 1.14 into 10 to power 6, very high Reynolds number. So corresponding to this, you can see your pressure recovery. So initially at first point, pressure recovery was less. Then when your Reynolds number increased, pressure recovery has started decreasing, and again when Reynolds number is high, then pressure recovery is actually increasing. So this is because the separation point, first it was shifting towards the starting, and again after the Reynolds number of 2.5 or close to 3 into 10 to power 6, it again started shifting towards the rear direction. Okay, so that's why we have more pressure recovery evident in this particular case. Okay, but one important point is, in case of flow over a sphere, when my pressure recovery is decreasing, so it means in the total drag force, which component is contributing more, form drag or skin friction drag? If pressure recovery is less, form drag will be dominating. So that's why in up to separation point is coming towards the upstream direction, we consider that contribution of form drag actually increases. But the moment separation point starts moving again back towards the rearward direction, then pressure recovery, then the contribution of the form drag starts decreasing. So this contribution you can clearly see in terms of this particular drag coefficient diagram. So here you can see this is the drag force as function of Reynolds number. So in this initial regime, you can check it with Stokes law. So up to this Reynolds number close to 1, your value of CD obtained from Stokes law will give you good correlation. But after this point, then it will follow the different curve. Okay, and in this particular range of Reynolds number, here you can see the value is almost constant, and this value is close to 0.445. Okay, and after this, here you get one important point. This is the point at which actually your separation point again starts moving towards the backward side. Okay, so in this critical transition range, where there is change of the location of the separation point, okay, corresponding to this you will be experiencing a drastic decrease of the drag, and again you will be having improvement in drag because you are having drag coefficient, because after this point you are having again the reattachment of the flow to the higher angles. Is this point clear? And these are the different correlations for drag coefficient which can actually fit data of the previous curve in different ranges of Reynolds number. So this is the previous is nothing but the master drag curve which you can apply for any situation, and the different Reynolds number portions of this curve can be obtained using these equations. Okay. And then one important point is, if we simply say that our flow, so this was when our sphere was stationary and flow was happening over the sphere. Now we can take reverse situation, like in case of raindrops. Okay, so we can say that our surrounding fluid is stationary but spherical solid is actually falling. Okay, so in that scenario what will be happening? We know that drag force will be of the order of buoyancy force minus weight. Is this one clear? So if you have a free fall situation, even at high Reynolds number, then also what will be happening? If you have a steady situation, so corresponding to steady situation, if your flow is not accelerating, then drag force will be balanced by buoyancy minus weight. Okay, so I can write that drag force will be equal to delta rho times G pi by 6 dq. Is this one clear? Now we know that drag force can be written in terms of CD times 1 by 2 rho ut square into area. Okay, so area will be coming projected area pi d square. Is this one clear? I can write drag force in terms of this value. All are clear with this idea? So now CD can be written as, what I can write about CD? Value of drag force I will be substituting this. So this value I will be substituting here. Okay, and right side I am having this. So if I do write these equivalence, then I will be getting CD equal to 4 delta rho GDQ by 3 rho into ut square. Is this one clear? And ultimately I can non-dimensionalize this equation in terms of Reynolds number. So if I have to make this ut d rho I am already having in terms of Reynolds number, then I will be getting one rho and one mu terms. So this is giving me the square of Reynolds number. Okay, and we know that in the range of 750 to 3.5 into 10 to power 5, my value of CD was constant and which was close to 0.445. Okay, so if I substitute this value, then I will be getting my terminal velocity in this range is 1.73 GD into delta rho by rho 1 by 2. So it means this can be the value of terminal velocity at high Reynolds numbers. Okay, and it can be written in terms of RET. RET means non-dimensional form. Okay, Reynolds number corresponding to the terminal velocity. So RET will become 1.73 times, and this whole quantity is written as ND, where ND is something which is called as dimensionless diameter, and it is called as best number. Okay, the value of ND is called as best number, and little multiplication of this best number with some non-dimensional parameters makes it Archimedes number. Okay, so that is something which I will not discuss, and ultimately ND can be related with CD and Reynolds number. So this is only applicable for this particular range of Reynolds number. But if my range of Reynolds number is outside this limit, then CD will not be constant and CD will not be known to me. So in that case, value of ND will become CD times Reynolds number T square, and which is this particular relation. Is this one clear? All are clear with this idea? You have to remember one thing, whatever this theory we have applied, this theory will be only applicable once my sphere is following a vertical path while it is moving in the downward direction. Okay, but you will be finding for certain cases when it is setting the vortex behind it, alternate set of vortices, then on a free fall sphere, what will be happening? Because of this vortex setting, it will not be having a straight vertical path in certain range of Reynolds number. It will be having this type of zigzag path. Okay, so once you have this type of zigzag path, then what will be happening? Your drag, there will be enhancement in the drag force and decrease in the terminal velocity. Is this one clear? So what I am saying, if you have a freely falling sphere, we know that at certain range of Reynolds number, it will be actually setting off the vortices in its rear end. Okay, when the amplitude or frequency of this vortex setting matches with the natural frequency of this system, then corresponding to that we will be feeling a situation of resonance, and there in place of following a vertical path, it will be following a oscillatory path, because if this vortex is leaving, it will move to this side. Then one vortex will leave, this will displace it to right side. So it is falling, but it is following a zigzag path. Okay, so because of this zigzag movement, okay, what will be happening? We will be having enhancement of the drag force, because now in place of moving in a perfect downward direction, it has to slightly displace the liquid in or any fluid in horizontal direction also. Okay, so because of that, there will be actually increase in the drag force and there will be decrease in its terminal velocity. So how that decrease in terminal velocity can be obtained? So for that, this particularly happens in the range of Reynolds number 10 to power 3 to 2 into 10 to power 5, and corresponding values of gamma. Gamma is nothing but density of particle divided by density of fluid. So density of solid particle divided by density of fluid. So when this gamma is close to 1, then particle is neutrally buoyant. It means because of the fluid, it will remain almost in the fixed position. But when this is greater than 1, then only this situation will occur. Okay. So corresponding to this, CD can be modified with this particular relation and NU can be modified with this particular relation, where on right hand side CD and NU are the corresponding values of CD and non-dimensional terminal velocity for normal vertical flow. Is this one clear? All are clear with this idea? So whatever the values you will be calculating for normal free fall of the sphere, if we modify these values by this term gamma, where gamma is nothing but marking the ratios of densities, then how my values of dimensionless terminal velocity nu dash and dimensionless drag coefficient are actually being altered, that is something which we can see here. All are clear with this idea? And then this is one elaborate chart which shows that if different particles of different densities, for example this particle is of 10 gram per centimeter cube to 0.5 gram per centimeter cube, okay, and if you have air as the surrounding fluid at 20 degrees Celsius, then what will be the value of terminal velocity for different particle diameters ranging from 1 micrometer to 1 centimeter. So these top graphs are for particle flow in air and bottom graphs are for particle flow in water. Is this one clear? And these are depending upon the density of the particle. Okay? All are clear with this idea? So you should know that at what range of Reynolds number or what conditions you will be having actually zigzag motion of a solid particle once it is freely falling in a medium. Okay, because when you are deciding, when you are say designing application something like fluidized bed reactor. So in case of fluidized bed reactor, what is your interest? Your interest is that your fluidized particle should not settle at the bottom. Okay, so you have to create some conditions so that particles should not fall freely in the vertical path, but they should take some zigzag path so that they are experiencing more drag and they are remaining in the suspended state. But say if you are designing some system for the separation of solid particles from a fluid, like in case of electrostatic precipitators, okay, so or even in other cases like bag filters. So there what is your interest? If say fluid is coming, particle is there, you have to create some situation so that particles can easily settle down in the system. All are clear with this idea? So depending upon the individual particle dynamics, you can decide that what conditions you can maintain so that you can enhance settling or you can actually diminish the rate of settling. Is this one clear? All are clear with this idea? So basically we are deriving some of the things from fundamental theories. At the moment it may appear that whatever I am teaching is actually purely theoretical and only the scientific people who want to do fundamental research, who want to develop some drag coefficient, who want to develop some relations for the terminal velocities, who want to theoretically understand at what point separation is occurring, for them only it is important. But this type of studies have significant importance even in applications. Okay, but it may not be directly visible to you, but whenever you will try to see the practical applications, there you will see that people are operating actually under these conditions only. Okay. Okay, so we will discuss quickly about the spherical fluid particles at higher Reynolds number in next lecture.